Hi everyone. Today we're going to learn about redox reactions. So redox, otherwise known as oxidation reduction. So oxidation reductions, again, AK for short, and not just me, but everyone refers to it as redox. So oxidation reduction is the chemical changes that occur when electrons are transferred between reactants. So those are the redox reactions. Redox reactions are the principal source of energy on Earth. So basically combustion of gasoline, burning of wood, burning, in quotation marks, of food in our bodies, all of these require oxidation reduction reactions. Now, oxidation. So we're going to go through the old definitions today, and then next class we'll learn about the more modern definitions. So the original definition meant that the combination of an element with oxygen. So here we have, we're seeing iron here. So elemental iron, we're adding oxygen to it, so plus the oxygen gas, and then we get our iron oxide here. So that would have been the oxidation of iron. Now, compounds can also be oxidized. So if you'll see here, this is methane gas, if you remember that from grade 11 organic chemistry. That's methane plus oxygen. And then we've got carbon monoxide and water there. So that would be another example there. Just looking here, 1 second. Yeah, okay. Now, reduction, on the other hand, would mean the loss of oxygen from a compound. So again, here we've got our iron oxide, our iron ore, plus our carbon, for example, and then we're going to go back to the elemental iron here. So as iron oxide loses loses oxygen, we would say it's reduced to metallic iron. So reduction, we call it reduction because that refers to the fact that when iron oxide is reduced to metal, there's a considerable decrease in volume, so you have less of it. So the amount of solid material is reduced. I just threw this picture in here because some of you are Minecraft players, right? So you'll recognize the iron ore and copper ore from Minecraft. Or maybe you used to play when you were younger. In reality, they don't look like the pictures here. So iron ore, this is iron ore in real life. And copper, we get this green color here because copper becomes oxidized when it hits the atmosphere, hits air. Anyways, we'll talk more about those things later. Now, oxidation and reduction occur simultaneously, so they're always happening at the same time. So no oxidation occurs without reduction, and no reduction will occur without oxidation. So they have to happen together. So next class, we're going to go through redox reactions in a lot more detail. But before we do that, we have to go through, we have to learn this concept of oxidation numbers. Now, and the oxidation numbers, we're going to use the oxidation number to do some learning about redox reactions. So this is kind of our first step here. Okay, so an oxidation number is defined as a positive or negative number assigned to an atom according to a set of arbitrary rules. So there are rules that we have for figuring out what oxidation numbers are. We're going to go through those today, and we're going to practice assigning oxidation numbers today. Now, usually it is equal to the ionic charge, but not always. There are some rules. Now, for example, you know how I regularly harp on you guys that if the ionic charge or 2 plus, for example, the 2 is written first and then the sign. So now you're going to understand why, because oxidation numbers have the sign first and then the numerical value. So sodium ionic charge, for example, is 1 positive, while the oxidation number is +1. So the sign goes before the number. So make sure you get that solidly into your head, because that's something where people can lose a lot of half marks on things, right? So make sure you're understanding the difference there. Now, rules for assigning oxidation numbers. Number 1, the oxidation number of a monatomic ion, so this would be one atom, okay, is equal in magnitude and sign to its ionic charge. So, for example, we've got bromine minus, so that's the ion for bromine, so that would mean the oxidation number is going to be -1 for an ion of bromine. Now, next we have iron 3+. the oxidation number is going to be +3. So when you have an ion sitting there by itself, the oxidation number will always be equal in sign and magnitude to the ionic charge. Okay, number 2, the oxidation of number of hydrogen is always going to be +1, except in metal hydrides. So metal hydrides would be when you had a metal bonded to hydrogen, okay? So for example, we've got NaH here, sodium hydride. So in this case, and I'm going to put the oxidation numbers on top here. When hydrogen is bonded to a metal, it is no longer +1. So hydrogen is always +1 except when it's bonded to a metal. In this case, I note that the sodium is +1, which means the hydrogen is going to be -1. Okay, so I'm just going to write the oxidation numbers on top, and we'll that's sort of common for figuring them out, and we'll talk more about that as we go here. Now, the oxidation for an oxygen is always going to be -2, except for in peroxides. So we've got H2O2. I'm just going to recopy it here. H2O2. Now, to do the oxidation numbers, you know that hydrogen is +1, and you've got 2 of them. So there's +2 coming from the hydrogen, so that means this has to be -1. So instead of -2, it's going to be -1 in peroxides. That would be, and I think that is also true for K2O2 as well. The oxygen would be -1 instead of -2. Now, the oxidation number of an uncombined element is always going to be 0. So what that means, if you have just, say you had a reaction where you've got copper plus, that whatever. This copper sitting there is a solid, it's sitting there by itself, so the oxidation number is going to be 0. And that is always going to be true. Now, put a little note here for Hofbrinkel. If you had chlorine gas, for example, plus whatever, the oxidation of the chlorine gas would be 0. So Hofbrinkel molecules will be 0, as well as when you have something in its elemental state there, in its solid state, usually will also be 0. Now, for any neutral compound, the sum of the oxidation numbers of the atoms in the compound must equal 0. So by sum, we mean if you add the numbers together, right? So we've got carbon dioxide here. Now, if we look at the oxidation numbers, you don't know what carbon is, but you do know what oxygen is. And what was the rule for oxygen? Oxygen is always going to be -2. So if you've got -2 for oxygen and you've got 2 of them, what is the overall charge coming from the oxygen? I'm going to break mine up into this little chart here. It's going to be -4, right? Because I've got 2 of them. So 2 atoms of oxygen, both at -2, will give me an oxidation number of -4. Now, the oxidation numbers of both the carbon and the oxygen added together has to be 0, because CO2 is a neutral molecule. There's no charge there. It's not a polyatomic ion. So for this one, this would mean I would have to have +4 coming from the carbon, and I've only got 1 of them, which means the oxidation number of the carbon is going to be +4. Let's do another example of that. So let's do magnesium chloride. Okay, so looking at that one, if we separate it here, chlorine, so it's usually they're going to be equal to their ionic charge. So chlorine we know is -1, and I've got 2 of them. So I've got -2 coming from the chlorine, which means I have to have +2 from the magnesium. There's only 1 of them, so the oxidation number of the magnesium is going to be +2. Good. Now for a polyatomic ion, the sum of the oxidation numbers must equal the ionic charge of the ion. So for an example, NO3-. Okay, so looking at this one. So I'm going to figure out what the oxidation numbers of nitrogen and oxygen are, and when I add those together, they should equal -1, because I have to have it equal to the ionic charge. Now, oxygen we know is always going to be -2. So I've got -2, and I've got 3 of them. So -2, -2, -2, I'm going to have -6. So I have to think, what number plus -6 is going to give me -1, because the sum of those two numbers has to equal the ionic charge. So this is going to be +5 here. I've only got one of them, so the oxidation number of the nitrogen is +5. Let's do another one. Phosphate ion, okay, so PO4 3-. If you look at this one, you have to have the oxidation numbers of phosphorus and oxygen being equal to -3, right? So let's do our little chart. Oxygen we know is -2, so -2, and I've got 4 of them, so this tells me that this is going to be -8. So what number plus -8 is going to give me -3, and we're going to have +5 again here. So the phosphorus here is also +5. Okay, I'm going to do a couple more here for you. I'm just going to erase this so I have space. All right. So what would happen if you have, let me think here. So sodium phosphate. So how you're going to do these, people do them differently. You can break them apart, so you know they're going to dissociate here, right? So you can break that apart into Na plus and PO4 3-, and then do the oxidation numbers there separately. Or you can, like, so when I'm doing this would take too long for me. So for this one, I want to just, oops, sorry. Oh, I pressed a button there. Yeah, yikes. Did not mean to do that. Okay. Sorry. So for me, the PO, it takes too long to break them apart like that. So I just like to think of the PO4, and I just remember in my mind that it's got the 3- here. So I would just go through, and I know that this is 2-, and I know that there's 8- there. I want to get to -3, so that tells me there's +5 there. Oh, geez Louise, there's supposed to be a 3 there. Sorry, guys. So now I know that sodium is going to be +1, and I've got 3 of them, and that's going to balance off the +3. And so now I'm all equal, because if I look through here, I've got 3 positive, 5 positive, and 8-. Those things all equal 0, right? And I can do it that way. Oops. Oh, why have I stopped working? Oh, now it's working. Technical difficulties. Oh, I think because that was from before. Yeah. Ah, okay, never mind. I'm gonna go here. Oh, what a day. Sorry, not one of my finer videos. Anyways, I'm gonna go through one more example here. We'll just use this. So, for example, let me just think of another one here. If we had, right, okay, so let's go H2SO4. So the hydrogen sulfate, or sulfuric acid, you're going to break it apart. If it dissociates, it's going to dissociate into 2H plus SO4 2-, right? So you can do those separately. Like you can do the hydrogen plus the hydrogen ion, or the SO4 2- separately. But like I say, I like to keep them all together. So it's going to break apart here. Now the sulfate ion, I know that oxygen is -2, and I've got 4 of them having a -8 there. So sulfate ion, remember, SO4 2-. So I need these numbers to equal -2. So I know that the sulfur has to be +6, because +6 minus, So this is going to be -8 down here with 4 of them. So +6 minus 8 is going to give me my -2. That's where that comes from. And then the hydrogen I know is going to be +1, and I've got 2 of them, and that will balance it out. So +1 for the hydrogen, +6 for the sulfur, -2 for the oxygen. Okay. Let's do one more. Now, if we do LiMNO4, so lithium permanganate, now this is going to be, if we find this MnO4 as a polyatomic ion has a charge of 1-. Now, I'm just going to do this one separate for you here. Now, if you do that, the oxygen we know is -2, right? Oh my God, I don't know why this pen is not working all of a sudden. Hold on. MnO4 minus. Okay, I know that this is -2. I've got 4 of them, so the overall charge is going to be -8, which means what does that manganese have to be? What number added to -8 gives me -1? +7. So the manganese has to have an oxidation number of +7. Now I'm going to just put them in here. So that's +7. Lithium is going to be +1. For the most part, the alkali metals are all going to be +1. And that's the oxidation numbers for each of them. So you have to practice those. You can Google other videos for that if this is still confusing for you. Exercise 4 is assigned, and the answer key is posted. So check your work, and then when you're in class, if you still have questions, we can go through things. You do want to get this skill down because we're going to use it in our next concept. Okay, thanks everyone.